Welcome to the last of the section 2.1 videos. In this video we're going to pick up with a third limit trick for solving algebraic limits that are somehow hard to solve. These are the examples that I'm going to go through. Before I show you what u-substitution is though, take a moment to solve the warm-up question here. Looking at that limit and thinking about the limits you did last night in your videos, what do you think this equals? Great, so you probably just saw that the limit is in fact 0.047, and a number of you may have accidentally thought that it was 1, so this is a really important clarification before we move forward. If you put that it was 1, you were thinking along the right lines, because sine of x over x does have a special limit that we have to memorize, but the limit of sine x over x only equals 1 at 0. So in your haste and pride over remembering this special limit, don't forget the details. In this case, at 3, well, you can just plug the 3 into this limit because there's no 0 on the bottom of the fraction. There's nothing that goes wrong. And you would want to make sure that you are in radians, but then you can just evaluate this numerically and you get 0.047 as an answer. So talking about u-substitution. This is a skill that you are going to use a million times in calculus. And here's the big idea. You should probably put the big idea down in your notes. The big idea behind u-substitution is you can use this trick when you think that you recognize the structure of the problem, but it somehow is a little bit off of what you expect. So for example, I think that I recognize the structure of this problem. This is saying sine of something over that same thing. And I think that I recognize that this is really similar to a limit that I know. In fact, take a moment and predict what you think this limit should equal. You don't actually know how to solve this, just take a guess. Cool, so maybe your guess was confirmed, maybe it was denied. Either way, guessing isn't good enough. You need a way to algebraically prove what this limit's going to be. The way that you're going to do that is u-substitution. So the idea is I'm going to change the variable here. In particular, I'm going to plug in a variable called u. And the way I'm going to change the variable is by choosing u to equal something very specific. In this case, I'm going to choose u to be a symbol that represents the same thing as x plus 4. And I can do that because I'm just defining a variable. And when you use u-substitution, you're always going to define the variable using the word let. So we're saying, well, let's suppose u means this. Well, the reason I chose this is because I basically am seeing that the inside of the sign is the same as the denominator. And I'm thinking to myself, if I can just say this is sine of something over that same thing, then I can use that special limit rule. The only trick is that if you're going to change the variable here and here, you need to change it in the limit as well. So what I need to know is, as x gets closer to -4, what happens to u? Well, as x gets closer to -4, then u is x plus 4, and u must be getting closer to 0. Really what I did in my head was I just plugged in that -4. If this number is getting closer and closer and closer to -4, this whole thing is getting closer and closer to 0. So, having done my little think aloud here, I'm ready to get started with the problem. And the next step is to rewrite a new limit. And my new limit, instead of having x, is going to have u. And this limit is going to go to the number that we determined in this little think aloud here. If we take x and we change the numbers and get closer and closer and closer to -4, then u, the answer to this little piece, is getting closer and closer to 0. And now, since I changed the variable at the bottom of the limit, I'm going to also change the function itself so that I can write sine of u. And the reason I can write that is because u is the same thing as x plus 4. And then I can write my fraction line, and on the bottom of the function, I'm going to put another u. And again, the reason I can do that is because we just said that u is the same thing as x plus 4. Well, we haven't changed the meaning of this function, but now we have a limit that we know how to evaluate. When we do this, this is kind of your thinking process, and you want to keep it separate from your final answer. But my final answer now is very clear. The limit as some variable goes to 0 of sine of that variable over itself is 1. And this last step I can take because that's the rule. You memorize this limit. Basically, this is the same thing as this special case. It's just got a different variable, and that's okay. You can call the variable anything you want. Let's review the important steps before we do another one. The first thing I recognize is that this structure looks similar to a limit I know. So I was motivated to try and change this limit so that it would look more like this. And the way I did that was I replaced this part that I saw repeated with a new variable u. And I made that replacement by defining u to equal x plus 4. And then I had to reason to myself, if we're no longer talking about x, what happens to u as x gets closer and closer to negative 4? And the answer was u goes closer and closer to 0. So that became the new region for my limit. I'm going to try another one because I know this is pretty unfamiliar. So let's look at the second example. Once again, you should notice the structure of this. We've got sine of something over something. This time it's not exactly the same, but it's pretty similar. So I'm going to define u, and I'm going to define u to be this thing inside right here. And my goal, of course, is on the next line to write sine of u. Now, if I'm lucky, I will have sine of u over like a u, because then I can evaluate the limit. Unfortunately, I don't have 3x on the bottom. It's not exactly the same thing, so I'm going to have to be a little tricky. If I solve this equation for x instead of for u, I can divide both sides by 3, and I could write x equals u divided by 3. And now I kind of have the tools. The last thing I need to check is, well, what happens to u as x goes to 0? As x goes to 0, 3 times x is also going to go to 0. So this is my thinking process. Again, we may not know exactly if it's going to work. This is something I'm trying. I'm trying to rewrite this limit with a new variable called u. And so the limit as u goes to 0, that came from right here, of sine of u, because I'm replacing the 3x with a u, over, now x is the same thing as u over 3. And this is not quite ideal yet. Really what I wanted to see was sine of u over u. It's not there yet, so I'm going to have to continue simplifying this limit. The limit as u goes to 0. And one way I can think to simplify this is we've got sine of u over u divided by 3. Well, that's the same thing as sine of u over u times 1/3. I'm just rearranging. And when you divide by 1/3, think about keep, change, flip. This is the same thing as saying the limit as u goes to 0 of sine of u over u times 3. Again, that's just what it means to divide by that little fraction. I'm just rearranging. Well, here's what's cool. Limit properties basically say that this is the same thing as the limit as u goes to 0 of sine of u over u times the limit as u goes to 0 of 3. This limit I know. I know that that limit is 1 because it's defined to be 1. This limit is the limit of a constant, and the answer is just going to be 3. So the answer to this whole limit is 1 times 3, which is 3. I would imagine some people got a little tripped up with the fraction here. Try not to focus on the algebra, focus on the big step, which was why did Miss MV choose the 3x, and what did she do with it in order to rewrite her limit? So those two examples have everything you need to know. I'm going to do two more just to give you a heads up that you shouldn't trip yourself up when you come across a situation like this. Because having just showed you this strategy, you might say to yourself, oh, okay, I need to define a u, and then you'll start working, and you'll realize halfway through that you've just been silly. Always go back to what you know about limits. I know that when we say the limit as x approaches 2 of this function, we basically mean, what does this function equal near 2? Well, for this particular function, I can just plug 2 in because there's no discontinuity. I can put a 2 on the bottom. Just because there's a fraction doesn't mean we need to do anything fancy. So actually, this limit is just the sine of 2 minus 2 over 2, and that's sine of 0 over 2. Sine of 0 is 0, and 0 over 2 is 0. We didn't have to do any fancy u substitution for that one. The reason why not is because we didn't have a 0 on the bottom to start with. Now for this second one, we do have a 0 on the bottom here. So if we're going to be able to solve this limit, we're going to have to use some sort of strange method to do this one. And we can try the u substitution. The smart choice would be to say, well, let's let u equal x minus 2 and try to rearrange what this looks like. As x goes to 2, x minus 2 is going to get closer and closer to 0. So I can write my new limit as the limit of u getting closer to 0. And then we need to rewrite this sine of x here. So what we did last time was we solved for x. So I would add 2 to both sides, and I would write x equals u plus 2, which allows me to substitute in a variable u instead of x. And my original goal was to replace that bottom with u. Now, this limit still looks something really close to sine x over x, but it's not exactly there. We really shouldn't have this plus 2 in the bottom. And looking at this, these two ways of writing it, neither of them can be evaluated. They both have a discontinuity at the bottom. This is an example of limit that we just don't know how to take. Maybe it exists, maybe it doesn't. We don't have any way of telling. We did the right job in trying to do a substitution. It didn't pan out, and that's what you get sometimes. Make sure that you have these examples written down, and then let's look at some for you to try out. After you try these out, when you hit play, I'll show you my answers. All right, here we go with the answers. For the first one, I chose u to equal 4x. And double check for yourself that you make sure you switch the limit right there, because if you don't switch the variable, that's a good way to get it wrong. For the second one, I was checking to see if you were paying attention. You don't need substitution or u substitution for this one. No need to change the variable because you can just plug 0 in. There's no problem. Make sure your calculator's in radians and you should get the same decimal that I do. Here are the last two, which took a little bit more work. I chose u equals x minus 5 because I recognized the structure here, and that gave me an answer of 1. And then for the last one, you have to do that added step because inside of sine and the bottom of the fraction aren't exactly the same. I set what u was going to be, and I decided u was going to be the 2x, and then x is the same thing as u divided by 2 because of this expression. I just rearranged it, which meant that I changed x to u over 2. And I found a different way to show my work than I did in the earlier example. Maybe this makes more sense to you. After getting to this point where I have the fraction on the bottom, I did keep, change, flip, keep the top of the fraction, change the division to multiplication, and flip the bottom fraction. And then hopefully you can see that sine of u times 2 over u, I just switched the denominator here. You could even do sine over 1 if that makes it easier, and the 2's on top. And then this is product rule, where I split it into 2 pieces, and you must actually do that. Don't skip from this line to the answer, because that technically doesn't count as proof. You can't just plug in something here, but you can replace this with 1 because that's a limit we memorize, and this is the limit of a constant. Make sure that you understand the terms, and let's talk in class.